Okay, so today we're going to talk about solubility equilibrium and the equilibrium constant for solubility. So, first we should talk about the solubility rules that we studied a little bit last unit. So, the solubility rules are a generalization. When we say something like all compounds with nitrates are soluble and all compounds with alkali metals are soluble, but hydroxides are not soluble unless they're with alkali metals or ammonium. When we say things like that, we do so with the understanding that the rule is these are soluble to make a 0.1 molar solution. 0.1 molar solutions are the standard solutions in our labs, and so that's what the solubility rules reference. Now, the truth is, any compound is soluble to some degree. Some are more soluble than 0.1 molar. Some are less soluble than 0.1 molar. So the solubility rules are just kind of a quick, generalized way to tell how soluble something is. But the reality is to figure out the real concentration, the real solubility of something, it's an equilibrium process. So we have to solve for the concentration using equilibrium. Okay, so to start off, anytime there's a solubility equilibrium problem, we write the reaction with the solid on the left. And this is what we call a dissolving equation or a dissolution equation, because we see the aqueous ions being released during the dissolving process. Right? So, number one, start by writing, you can also call it an ionization equation. Okay? So, with solubility equilibrium, because it's an equilibrium process, it follows the same laws that regular equilibrium problems follow, meaning that we can write an equilibrium expression by taking the products over the reactants. And that's what's going on here. Rewriting it in a way that you're familiar with seeing, we would write it this way. Concentration of the products over the concentration of the reactants Now, if you remember one of the rules, solids and liquids cannot be expressed in an equilibrium expression. So that means we ignore it. That means we do not write the equilibrium expression with it. So I'm just going to erase that. And so this is what we call this KSP, the constant for the solubility product. And it works just like equilibrium constants do. If there's a large value, that means there's more product than reactant at equilibrium. If there's a small value, that means there's more reactant than product at equilibrium. All the same rules apply. So, for starters, let's write dissolving equations for these two compounds. Go ahead and pause the video and write it out and see what you come up with. Okay, so I'm going to go ahead and write this out. Barium chromate. Chromate is CrO4 with a -2 charge. Barium is +2 ion. So that's the formula. We get the barium ion, and we get the chromate ion. Change colors here for the silver. The silver phosphate So these are the dissolving equations. Okay. So the first type of problem is to find the KSP value if you are told the solubility. Now, reminder, the solubility is otherwise known as the concentration at equilibrium for a solid. So, if they're telling you solution is saturated, remember the word saturated is code. That means at equilibrium. So they're telling you the saturated solution of silver bromide has a molarity of 7.1 times 10⁻⁷. Find the KSP value. So follow these steps. The first thing, write yourself an equation. So silver bromide, you got to look up the charges so you write the formula correctly. It's +1 -1, therefore that's the formula. The dissolving equation. I'm not going to write the AQs anymore because if it's charged, the AQ is assumed. So there's our equation. Write the expression. So products over reactants, neglecting solids and liquids. So the KSP would be found by taking silver concentration, and of course, remember these are at equilibrium. These are equilibrium concentrations. Okay. All right. So we can go ahead and substitute in. Earlier, they mentioned the molarity of AgBr was 7.1 times 10⁻⁷. That was told to us. So, if we look at the mole ratio, I'm going to do this in orange, the mole ratio between the silver bromide and the silver bromide and the bromide, it's all 1:1. So if they're telling you the concentration is 7.1 times 10⁻⁷ molar AgBr, for every 1 mole of AgBr, there's 1 mole of Ag, which means the concentration of silver at equilibrium is 7.1 times 10⁻⁷. Likewise, it's going to be the same for the bromide because it's the same ratio. So that means we have both of those concentrations. So we just plug them in. So KSP value will be 5 times 10⁻13. All right, so that is the first type of problem with solubility equilibrium. It's finding the KSP value if you know the solubility. All right, the solubility has to be told to you, and here it was told to us. They didn't call it solubility. They said it was saturated, but if it's saturated, then you know that this concentration is the solubility, because this solubility is the concentration at equilibrium. The second type of problem is to go the other way, is to find the solubility if you know the KSP. So, let's try this one here. What's the solubility of lead chloride if the KSP is given? All right, so first things first, write an equation. Lead chloride, PbCl2 okay, note the mole ratio, right? PbCl2, so 2 chlorides are released. So there's our equation. Our expression would look like this. Remember that if there's a coefficient, the coefficient becomes a square. All right. So if we want to find the solubility, we need to solve for these what's in these brackets here. So, in thinking about this in terms of an ice table, what could we substitute into these brackets? Well, I'm going to rewrite this because I didn't give myself enough room, but let's do this. I'm going to rewrite that equation here, just so you can see. All right, so under an ice table for solubility equilibrium, nothing goes under the solids. All right, so just put a big X there. There's nothing here at the beginning, but we know that we're going to add to the product side, and what we don't know the value is we use X. So that's my ice table, and that's at equilibrium. So, since KSP is equal to the concentration of lead at equilibrium times the concentration of chloride at equilibrium squared, we have values that we can plug in because we were told the KSP value. So 1.7 10 to the negative fifth is equal to the concentration of lead at equilibrium times the concentration of chloride at equilibrium squared. And the values that I found from my ice table are X and 2X. So therefore, we need to find X. So quantity 2X squared is going to be 4X squared times X. This is going to be 4X cubed. All right, so use a calculator. You don't really need solver for this one. You can just solve for X, so divide both sides by 4 and then take each side to the 1/3 power. So 0.016 is the value for X. And X was assigned as the value for the lead ion. And what is the mole ratio between lead and lead chloride? It is 1 to 1. So therefore, the solubility of PbCl2 is equal to 0.016 molar. All right, so we learned how to solve for the KSP value if you were given molarities and solubilities, and then we learned how to find the solubility if we were given KSP. In all instances, you should start by writing the equation, you should write the expression, and then an ice table might help you figure out what you plug in when you're solving for the values.